All right, so we're going to begin talking about um, chapter 4.2, which is measuring the strength of association with correlation. Um, so let's talk a little bit about correlation and the meaning of correlation. The correlation coefficient is a number that measures the strength of a linear relationship. The symbol used is R, and the number is always between -1 and +1. R values close to -1 or +1 indicate a strong linear association. R values close to 0 indicate a weak association. So correlation coefficients of 1 and -1 indicate perfect positive and perfect negative associations. In other words, the data points lie exactly on the line, as can be seen in these two cases. This is a perfect slope of -1, and this is a perfect slope of +1. Now, visualizing the correlation coefficient. Notice in these cases that as R increases, there is less vertical variation in the data. In other words, the trend is stronger. So right here we have an R value of 0.072, and we can see that there's variation in the vertical data, but um, not as much as if it were a perfect one. In the second case, correlation coefficient of 0.48 indicates that there is a positive correlation, but it's not exactly, the variation on both sides is greater than in this case here where it's smaller. In other words, the trend is weaker. And 0.19, although this is a positive coefficient, it's very weak. It's still trending positively, but it's very, very weak because it's so spread out around that line. So that makes the coefficient closer to 0 instead of closer to 1. Now we're going to learn about computing the correlation coefficient. I'm going to show you two different ways to do that in a little bit. Data are converted to these z-scores, which are multiplied together. These products are then added, and the resulting sum is divided by n-1. In practice, correlation coefficient is found using technology. In other words, we don't do it manually. Now, here is a table that represents the heights of 6 women and their weights. So I'm going to write these down on a piece of paper because I'm going to have to show you both ways to do them. 104, 110, 141, 125, 170, and 160. Okay, now let's look first at using StatCrunch. So in your homework, you'll be able to just click on the data, and you'll be able to transfer it directly to StatCrunch. I'm using StatCrunch independently, so I want to go to StatCrunch here and put in my data manually. Okay, so to do that, I'm going to go ahead and type in my numbers. use two separate lists, one for the height. So in this case, I have 61, 62, 63, 64, 66, and 68. And then I'm going to put in the weight, which is 104, 110, 141, 125, 170, and 160. Next, I'm going to go to the Stat button and go down, scroll down to regression and press simple linear regression. Select the first group as the X variable, the second column as the Y variable, and press compute. And right about there, you can see the correlation coefficient. I'm going to snip that page out and bring it over so you can see it in the notes. They already have it in the notes, but I like when I do it by hand to bring it out here. There's a lot of information here, but I'm going to put it next to the one that we have that they did here and see if our numbers compare. Oop, that didn't work out. Let me see if I can pin it on the side here. Yeah. All right, there it is. And you can see the numbers are identical. We can see the coefficient right there is 0.8809, 0.8809, and then they would ask you for the, to do it to a certain number of decimal places. If you wanted to see the graph, you can actually go back to StatCrunch and view the graph for this by pressing the right button, and you can see your graph there for this particular set of data, your scatter plot. Isn't that nice? I'm going to copy and paste that also so you can have it in your notes and look at it. Okay. So yeah, you can put your graph in there as well and get your fitted line. StatCrunch is a really handy tool for doing this stuff. Now, I also want to show you how to do this. It didn't. Okay, there it is. And you can see that we have a graph of it similar in the StatCrunch output. I also want to show you how to do the same set of data using your calculator. The printed instructions are here, but there's a couple of things that you have to do when you use the calculator for this. So we're going to go ahead and get out of this list by pressing second quit. And the very first thing you want to do when you're doing correlation coefficient with your TI-84 calculator is to access the catalog by pressing second and 0 and scrolling down until you come to diagnostic. This is a one-time set, and your calculator may already have it set. If it doesn't, then you're not going to get the result that you want. Okay, so scroll down to diagnostic, maybe somewhere down the list. Okay, right here, right? Okay, here we go. Diagnostic. I scroll right past it. And you want diagnostic on, enter, and it says done. All right, so now we're ready to put in the set of data. So go to Stat, Edit. So I have some data in there from a previous problem, I'm going to go up, clear it, and press enter to get rid of it. And then I'm going to put in the new set of data, 61, 62, 63, 64, 66, and 68. And then for my second list, I'm going to put in the weight, 104, 110, 141, 125, 170, and 160. Okay, press that again, calculate, and select number 8. And keep pressing enter. It will do the calculation for you. Okay, and this is the screen that you will see. I'm going to copy it over and paste it into the notes. So notice again that the correlation coefficient is the same as if we computed it with StatCrunch. Okay. All right. Now let's go ahead and look at other stuff on this here. So changing the order of the variable does not change R. Important note, okay? Changing the order of the variable, in other words, if we were to put in the previous example, if we were to do the weight before the height, it doesn't matter. It doesn't change R. It doesn't matter which one you pick as X and which one you pick as Y. Adding a constant or multiplying by a positive constant does not affect R. So if I were to multiply each of those heights and each of those weights by 3, it doesn't affect the value of the correlation coefficient. R does not have a unit, and R is only useful to measure linear trend. Always graph your data before computing R to make sure the association is linear. So sometimes we would assume that it's linear based on the type of problem that we're given. All right, so let's look at a couple of problems here. This is from your homework. I'm doing some of them. The scatter plot to the right shows the college tuition and percentage acceptance of some colleges. Would it make sense to find a correlation using this data? This data is not linear. Okay? Now, no, linear regression is not appropriate because the data is not linear. Simple question. In this case, the data is linear. So yes, it would make sense to do linear appropriate to calculate the correlation coefficient because the data shows linear regression. Okay, it's a there is that the correct answer? Yes, there is no reason why linear regression would not be appropriate because the trend is linear. So clearly linear regression calculation would be appropriate. The figure shows a scatter plot of birth rate, live births per 1,000 women and the age of the mother in the United States. Would it make sense to find correlation coefficient for this data? Explain. So clearly this is not linear. It goes up and then it goes down. So the trend is not linear. Okay, be careful which one you pick for the no here. There is enough data points, but the trend is clearly not linear. On the basis of the scatter plot, how would you describe this data here? Positive, negative, or near zero? So if you look at the data, it's kind of trending that way, yeah? Kind of trending there. I would put it as positive. Matching scatter plots here. So we're given some numbers to choose from. Okay, we're given some numbers to choose from. In the first case, this data is very scattered. It might almost be a weak. So we're going to pick the one that's closest to zero, which is negative 0.204. Then this one is positive. So we're going to pick the positive choice, 0.631. And this is negative, so we're going to pick the negative choice that's closer to -1, which is negative 0.889. All right, question 12 is kind of a repeat, so I'm going to leave that one for you guys. Okay, question 13. The table to the right shows the number of people living in a house and the weight of trash. So I'm going to do this both ways. I'm just going to do this with the calculator, and then I'm going to show you how you can do a similar problem in StatCrunch, okay? So let me write the data down, and where is this data? At question 13, yes. All right, so I'm going to go ahead and put that data into my calculator. Okay, so remember stat, edit your list. So clear the first list, and then clear your second list. And then I'm going to enter the data. People, 1, 2, 8, 2, 7. And then on the next column, I'm going to put in the weight of trash, 23, 25, 97, 24, and 85. Okay, now remember our process. We already set up our diagnostic on. We don't need to do that again. Stat, calculate, number 8, and hit the enter button until you can get to your answer. So we see the correlation coefficient here is 0.994 at the 3 decimal places. I'm going to capture the screen and put it in our notes. Okay, and we're going to go ahead and talk about this just a little bit. Okay, so we can write the correlation coefficient is that number there. They want it to 3 decimal places, so 0.994. Okay, and now the question continues. Suppose some of the weight from the container, each container weighs 5 pounds. Subtract 5 pounds from each of the weight and find a new correlation of the number. What happens to the correlation? So we know already that adding or subtracting a constant does not affect the correlation coefficient, even if we added -5 to each number. So that correlation coefficient would pretty much still be the same. Okay, it will still be 0.994, because the correlation coefficient remains the same when a constant is added to it. So where is that answer? C, 0.994. Sorry, that's A. Yeah, A. And suppose each house contained exactly 4 times the number, but the weight of the trash was the same. Again, multiplying by a constant does not affect the correlation coefficient. So you're wasting your time if you try to multiply each number by what did they say here, 4 times? That's just wasting your time. To do that, you can try it. Good luck. The correlation remains the same when the numbers are multiplied by a positive constant. Okay, and the correlation remains the same when a constant is added to each number. I want to just show you a similar problem in my lab. Question, where is it? Question 13. Okay, here we go. So if I were doing question 13 in 4.1, sorry, 4.2, and I didn't want to use my calculator, I simply pressed the little button, click the copy table, open in StatCrunch, and there I would have my data. Remember how you do this: stat, regression, simple linear. Remember, it doesn't matter which one you select for Y, but don't select the same one like I did here. It doesn't matter which one you select for X and select for Y and compute, and you would get your correlation coefficient right there. In this case, it's 0.986. Okay, so that would be the way you would do this problem in StatCrunch, by, when you do your homework. All right, now let's continue here. So moving on here. 5 people were asked how many female first cousins they had and how many male first cousins they had. And there's the data, female and male. And we're going to, I'm going to use the calculator for this one because it's more convenient. If you guys want to use StatCrunch when you open up the program, that's fine. So I'm going to go to Stat, edit my list, clear my list, clear my next list, and I'm going to put in the data: 2, 1, 4, 5, and 3. Then in the next table, I'm putting in for the female 5, 1, 1, 8, and 2. Stat, calculate, number 8, enter, 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 enter. Okay, so now we can see that we have a linear coefficient, a correlation coefficient of 5.518. I want to go ahead and copy that and put it into our notes. Actions, capture the screen, copy, paste it into the notes. And they're asking for this in 3 decimal places, so 0.518. Comment on the meaning of this correlation coefficient. So this is generally positive. People with many female cousins tend to have many male cousins. That's all this is telling us, this one right here. People with many female cousins tend to have many male cousins. Don't know if that's true or not, but that's what we came up with, yeah? All right, these are from the notes, so I'm going to leave them for you to try, okay?